I'm going to start with a slide we've seen several versions of already, which illustrates broadly the correlation between large igneous province eruptions and mass extinctions throughout the Phanerozoic. And what we've also heard about over the last few talks is that there's a lot of uncertainty in terms of what the actual processes that might relate these two things together are. And one thing that is very certain, I think, is that in order to figure this out, we're going to need very high precision time constraints on the sequence of events surrounding these mass extinction events and large igneous province eruptions to sort out the details of what the actual driving mechanisms might be. And so I'm going to focus on a case study, work I've been involved in over the last 8 years or so around the end Triassic mass extinction event and its potential link to the Central Atlantic Magmatic Province. So about 15 years ago or so, it became more obvious that a series of mafic dikes, sills, and flows that are now bordering the Atlantic Ocean may have actually erupted around the same time, and this became known as the Central Atlantic Magmatic Province, and a series of studies carrying out argon dating on a number of these lavas and intrusions showed that this broadly overlapped with the existing time constraints for the end Triassic mass extinction. And through this, or I guess a series of parallel efforts over the last 8 years or so, I've been involved in correlating events recorded in a series of marine sections from Peru, and biostratigraphically and geochronologically, and trying to correlate these with environmental proxy records globally, and then eventually with the actual eruption of the large igneous province. So this is just a map of the locations where a series of sections are exposed along a road near Levanto, and there's lots of volcanic ash beds within these sections which we were able to separate zircons from. And so this is a summary diagram to summarize a whole bunch of work that's occurred over the last 8 years or so. And what you see on the y-axis here is a composite stratigraphic section in meters that spans from the Upper Triassic, the Norian-Rhaetian boundary, up to the Hatangian-Sinemurian boundary near the top of the section here. And each of these red arrows here correspond to ash beds that we were able to get zircons out of. And then over here, the sections are also rich in important biostratigraphic tools in which we can put together the sequence of events in terms of biologic evolution, focusing here on the end Triassic extinction. And then these can be correlated both geochronologically and biostratigraphically with chemostratigraphic records from around the world. And so what's come out of this work is partly a high-resolution time series for the end Triassic through the early Jurassic. And then this can be compared to recent work out of MIT by Terry Blackburn and Sam Bowring in conjunction with Paul Olson and others that show that the extinction interval shown here in blue broadly correlates with the eruption of the Central Atlantic Magmatic Province down to, say, the 10,000 to 100,000 year level. And what I'm going to do for the rest of the talk actually is focus in on this area right here, right around the end Triassic mass extinction, and talk in more detail about some of the details of the geochronology, assuming most people in the audience are not geochronologists and may not be aware of some of the problems that we face as geochronologists trying to provide ever more precise time constraints for these events. So the question we need to ask is, what sort of time constraints do we actually need to answer these questions adequately? This is just a summary figure from Paul Wignall's paper from 10 years ago or so that summarizes the potential durations of environmental effects that may arise from large igneous province eruption, from global warming related to CO2, which may operate over thousands to 100,000 year timescales, to the very short timescale effects of, say, ozone depletion, acid rain, cooling from sulfate aerosols, et cetera, that we heard a bit about in the previous talk. So the take-home message from this is that we absolutely need time constraints of 100,000 years or better to actually start figuring out which of these potential drivers of mass extinctions might be most important. Okay, so how can we actually do that? So the tool of choice for most of these studies is ID-TIM's uranium-lead geochronology, in part because of very high precision that we can obtain. So it's pretty routine now to get 0.1% uncertainty on a single analysis. So say a single zircon or a fragment of zircon, or even better. And so if we want to then get 100,000 year uncertainty, so this is the uncertainty here in millions years, so this is our target. We want to be below this line. And of course the absolute uncertainty on our dates will increase with the increasing age. So if we want to look at a single zircon analysis, we can do this up to about 100 million years, and then our age resolution decreases. And so the common approach will be then to take weighted means of more zircon analyses in order to push the precision down into this realm. So if we're willing to spend the time measuring 100 zircons by ID-TIMs, which most of us aren't, then we can obtain this level of precision throughout the Phanerozoic. However, for more reasonable numbers of analyses, we're going to have trouble beyond about 200 million years actually obtaining the precision necessary to look at these processes in detail. Okay, so that's all good. We can analyze more zircons and get higher precision time constraints. The issue with doing this is illustrated in part from this figure, which shows age on the y-axis. These are analyses, or I guess PDFs, probability distribution functions for analyses by U-series dating of very young high silica volcanic eruptions. So these are zircons, and the distribution of zircon ages from these eruptions relative to the actual eruption age, which for each of these little panels is indicated by this vertical line. So the take-home message here is that in some of these eruptions, the ages of the zircons overlap very well with the actual age of eruption. But in many of them, older zircons are inherited from either the magmatic system at depth or within slightly older eruptions that are in the volcano. So you're getting a large mix of zircons in many of these eruptions, which often predate the actual eruption. And in the case of calibrating the stratigraphic record, what we really want is to know the age of eruption. So this implies that if you go back in time, where our absolute age uncertainties become larger, and then we take weighted means of many of these zircons, we could be biasing our dates, which then will be very high precision, older than the actual eruption. So this is something we need to think about in detail. So here's an example from right around the Triassic-Jurassic boundary that sort of illustrates this in terms of not a young eruption, but eruptions we're looking at around this. So these are data from Peru. Two examples of zircon data from the exact same sample. We published these data in 2008, and then published these ones in 2010. And the difference between these two data sets result, at least in part, from a new uranium lead tracer, which was put together by the Earth Time effort, in which we, by introducing new synthetic isotopes, or more isotopes into the tracer solution, we're able to eliminate the uncertainty due to mass fractionation during analysis. So the point here is that these data published here are less precise. These are all single zircon analyses where the height of these little bars reflect 2 sigma uncertainties in the analysis. And so between these two publications, we have very different uncertainties in terms of the single zircon analyses. And this horizontal line here reflects our best estimate of the time for the eruption of the North Mountain basalt, which is the lowest most basalt in North America related to the Central Atlantic Magmatic Province. So in terms of how you interpret these data, the implications can be very different. In this study, we took a weighted mean of these because it looked like a homogeneous population, and you find that the resulting age for the eruption of this ash bed, which is very near or within the extinction interval at the end Triassic extinction, does not, it actually predates the eruption of the basalt. In the subsequent data set, what we ended up doing was choosing the interpretation where the youngest zircon actually best represents the timing of eruption, knowing that because this data set with higher precision age constraints became much more complicated and may be and this may be due to pre-eruptive zircon growth, which in this case could have biased the weighted mean too old. So the difference between these two results has perhaps nothing to do with the analytics involved in the measurements, but the interpretation of the data. Now, the limitation of this interpretation of taking the youngest zircon from an eruption is that if we're just using one analysis, we're very limited in terms of the precision we can actually obtain. And so we're left with the question, if we want higher precision time constraints, how do we do that, knowing the complications that go into the actual zircons that we're measuring? And so I'm going to run through a couple ways that we're trying to deal with this, just as examples of potential ways forward. Bringing other data to the problem could be useful. And this is a diagram outlining the workflow in IDTIM's analysis, where we have zircons. In this case, we've made a CL image of it and then broken it up, and then we dissolve those little fragments in acid and place it through ion separation, where we separate uranium and lead and then put that in a TIMS, and then we take the remaining liquid from the column chemistry, and then we can actually analyze that for the trace elements within the exact same volume of material that we dated. And that could provide additional information, both in terms of the sources of the zircons or potentially the evolution of the magmatic system over time. So what might that look like? What might be some expectations from doing this? So if we have some igneous melt at depth beneath a volcano, and this is undergoing fractional crystallization or some other type of igneous process, be it assimilation or mixing of magmas, you might expect some evolution in the melt through time. In this case, if you're fractionating plagioclase from the liquid, you'll develop a europium anomaly in the liquid that could then be reflected in the zircon. So once you start crystallizing zircon, you may develop a europium anomaly as well, and then in eruption, you'd perhaps inherit zircons that crystallize over a period of time in this liquid. And then this evolution in europium anomaly would tell you that those with less of a negative europium anomaly may predate eruption, even if you can't resolve this with your analytical uncertainty in terms of the age. Here's an example of where that might be illustrated. This is thorium-uranium ratio, which you get out of any IDTIMS analysis anyways, but it illustrates that you can see evolution. This is actually pretty typical to see in plutonic rocks, where the thorium-uranium ratio in zircons goes down through time. So in this case, this grain is broken. The fragments closer to the rim are younger, as you'd expect, and they have a thorium-uranium that's lower. This is from a plutonic system in northern Italy that's about 30 million years old. If you go back to 200 or 300 million years old, your analytical uncertainties in terms of age would be much bigger. You wouldn't be able to resolve the age differences between these different zircon fragments, but you would be able to resolve the thorium-uranium ratio. So it puts the expectation out there. If you have this geochemical information, and you want to take a weighted mean of analyses, if you can't actually resolve the age difference, you could use the geochemistry as a guide. In other words, if you're going to take a weighted mean of these things, they better have the same geochemical signature if it's going to meet the assumption that they crystallize from the same liquid beneath a volcano immediately prior to eruption. So what do you see in ash beds? Here's one example of an ash bed near the Triassic-Jurassic boundary from New York Canyon in Nevada. And this is yttrium-hafnium ratio, scandium-thorium ratio from these zircons. And basically, it's a mess. This is very typical in ash beds from other data sets as well. And the take-home message here, I guess, is that despite, let's focus on these white squares, despite the fact that these all overlap within age uncertainty, the geochemistry of these zircons is very different, and we may want to be skeptical then about taking weighted means. These zircons could come from very different sources, be it in the magmatic system or have been incorporated from slightly older eruptions in the eruptive column. However, a subset of these analyses actually have the same age and the same geochemistry. So perhaps we're more comfortable taking weighted means of these grains to actually increase our analytical precision without making assumptions, or as many assumptions, about the origins of these zircons. So these are consistent with a cogenetic origin for a subset of these grains, and then maybe we're more confident. So if you do that, you can increase the precision of your estimated eruption date from plus or minus 0.13 million years to plus or minus 0.08 million years. So a 40% increase, something like that. And given that our target is at least 100,000, plus or minus 100,000 year precision, this is a way forward. Okay, so another thing that's not often exploited in uranium-lead geochronology is somehow building stratigraphic superposition into our age interpretations. This is always done on a qualitative level, in that if you have a series of zircons that are stratigraphically higher and they come out older, you know something is wrong, right? And the question then is, can we take this principle and build it into our age interpretations in a way that reflects the probability distributions of eruptions from each individual ash layer? Here's a hypothetical stratigraphic section. Here's age. These are our best interpretation for the eruption of given ash beds, and here's stratigraphic height. This is fine because they all overlap. It's not violating stratigraphic order. However, it's exceedingly unlikely that the age from this ash bed is actually here, given that there's a high probability that it's older than down here. This is better illustrated if you actually look at the uncertainty distributions rather than just error bars, and that you see the error distributions. These are assumed normal Gaussian distributions, and it's exceedingly unlikely that this is actually the eruption age of that ash bed. So we can build this in to an age model by Monte Carlo techniques. So if we take 1 million dates for each ash bed with a normal distribution, and then pick a random point from each of them, we can then put these in sequence, and those that violate stratigraphic order, here in pink, meaning for that point we picked from the probability distribution, it gets older as you go up. Those are unacceptable. However, a certain subset of these are acceptable. So you can throw out those ones that violate stratigraphic order, and then take the ones that are acceptable and calculate new means and uncertainties. So if you do that through this stratigraphic section where we have a high density of ash beds right near the Triassic-Jurassic boundary, it ends up improving age precision by up to 50% in some cases. This is most effective where you have densely spaced ash beds. And it's probably intuitive that if you have two ash beds that are not close together and don't overlap at all, this method doesn't increase precision at all. So it is illustrating that having more ash beds is, of course, useful, which probably is obvious anyways. So these methods have been employed in other studies as well recently in order to combine argon, uranium, lead, and cyclostratigraphic data sets. But they've been used for a long time in terms of radiocarbon dating, where they have very non-parametric uncertainties in their age estimates for layers through stratigraphy. So these are not new techniques, but they're very seldom employed in deep time by geochronologists. Okay, so I've focused on a couple ways of increasing precision in our data sets without making assumptions that we're kind of skeptical of, including weighted means of large data sets. But I haven't talked much about accuracy in terms of, as we go to higher and higher precision dates, we also want to be sure that we're not losing accuracy as we do that. So we can approach this because we've published data from the lowest, most camp basalt in North America, the North Mountain basalt. I showed you one date from that earlier. So this has been redated several times, and we can use this as a case study of how to actually evaluate accuracy of our dates through time. So this is an example of Terry Blackburn's study, which puts high precision time constraints on the entire eruptive sequence of the camp in the Newark Basin and in Morocco. So we can compare dates from about 2006 to now for the North Mountain basalt, and you can see that they don't all agree. And in the case of this older date to these dates here, we know the reason. We're using a new tracer solution, and the calibration of that tracer solution is important. The date from here, from this paper in 2010, and then the more recent study, the dates don't quite agree. And to be honest, we don't know the exact reason for that, but we have a list of possibilities. This here is the onset of the marine extinction from the Peru data. So in either case, we're overlapping with the marine record in terms of the extinction very well, but in terms of quoting precision of plus or minus 20,000 years on these, we're faced with, I don't want to say problems in terms of accuracy, but challenges in terms of doing this better and better in the future. And so many people here have probably heard of the Earth Time Initiative, and this has been really monumental in the last 10 years in terms of getting different labs, both uranium lead and argon labs, to work together in terms of tackling these problems with precision and accuracy. And the goal of that initiative 10 years ago was to have labs agree at the 0.1% precision level. Now we're talking about, the differences I'm talking about are at the 0.01% level. So we met and surpassed that original expectation. Now as we ask more acute questions about mass extinctions and their drivers, we need to address things that perhaps we didn't matter 15 or 20 years ago. But now they're becoming very important. And so there's more work to do, and that's a good thing, or we'd be out of a job. Okay, so I'll leave you with the conclusion since I'm out of time. Thank you very much.